All right. Hi, everyone. Good morning. Good morning, Prakash. Good morning, Aravir. Yeah, hi, Agnev. Good morning. Hi, Avni. Hi, Vedant. Good morning, everyone. All right. So, how is everyone doing? कैसी चल रही है आप लोगों की बोर्ड्स की preparations? प्री बोर्ड शुरू हो गए कई schools में? Some have postponed them. Good, good. I think number of attendees today are lesser because of exams in certain schools. Generally, otherwise around 90 plus participants रहते हैं. I'm sure it's because of the school examinations. All right, so as a quick recap, let's just quickly look through that what all we did in the last class. So I had started the Bohr's model of atom with you, started with its postulates, and then we spoke about the mathematical results, right? Radius ka, speed ka, and energy of electron in nth orbit. Like these were the three important results that I had shared with you, and I think we were able to derive the first two regarding the radius and the speed. And while doing this derivation, like I had mentioned in the last class also, that there are certain concepts of physics which I am using directly. These are something which you should be following in a sequential manner. Like when you study circular motion, when you study electrostatics, these concepts of angular momentum, centrifugal force, electrostatic force of attraction, these all come to you naturally in a sequential method. But while doing those derivations, I had taken that jump and derived these results for you. Now, at this point in time, I'm sure the derivations might look alien to you because of the way in which these formulas have been used directly. However, trust me, after studying these concepts in physics, this will be the simplest kind of derivations that you will come across. Like this is going to be very very easy looking back. Then after getting the results of speed and radius, I decided to expose you to certain kinds of problems that come in Bohr's model of atom. And we went in a learning curve method wherein we started with the simplest kind of problems first, like related to the direct use of the formula, and then increasing the difficulty to using proportionalities, saving time while solving questions. We, you know, compared two cases, only focus on the proportionality and then moved on, right? And then I introduced you to two other results, which is say time period of revolution, how much time does electron take to go around the nucleus in a particular orbit, and frequency of revolution, right? These were some additional results which weren't direct results of Bohr's model of atom, but because of basic knowledge of physics, we can compute them based on our results that we derived from the Bohr's model. Great. Now, अभी हमारा बोर्स मॉडल का एनर्जी का डिस्कशन बचा हुआ है, राइट? दिस इज इन फैक्ट the most crucial discussion in Bohr's model of atom because this is what got validated experimentally. Okay, this R and V, this was not something which was experimentally validated because honestly speaking, we could not see the electron, we could not see its motion, and direct measurement of this R and V was not something which was done. It was this third result related to the energy of electrons in orbits which got experimentally validated. So we will talk about that today as well. All right. So let's continue our discussion. Let me put the heading. Bohr's model only. Now let's talk about this third result. Let me label it as the third result, which was energy of electron in nth orbit, and sometimes we actually call it energy of orbit. So this is kind of initially confusing to a lot of students that like, is it the energy of the electron or is it the energy of the orbit? So the answer is it is actually the energy of the electron in that orbit. However, even if electron is not present in an orbit, we still talk about energy levels of these orbits. Let's say even in hydrogen atom, मैंने आपको starting में बताया था, like even in hydrogen atom, naturally electron will be present in the first orbit. That will be the natural or the ground state, we say. However, it does not mean that these other energy levels, they do not exist around the nucleus. They do, and the electron can excite or de-excite between them, right? So that's why we kind of use this term energy of nth orbit also. Now, as a quick calculation of the energy of the orbit, the total energy of the orbit can be written down as the sum of kinetic energy and potential energy of the electron. Right? What is this potential energy due to? Is it some gravitational potential energy? Or what is it? Where is this potential energy coming from? Correct. Electrostatic. Potential energy because of interaction between positive and the negative charge, positive charge of the nucleus and the negative charge of the electron. Now, kinetic energy, if I write half mv square, does it concern anyone? Like, is it a problem, or everyone is comfortable with putting kinetic energy is equal to half mv square? I hope everyone is very, very comfortable. However, again, thoda sa, I will ask you to again take a leap of faith with me. When I will be writing electrostatic potential energy, it will be K Q1 Q2 upon R. So K is the electrostatic force constant. Q1, this was the charge of the nucleus, right? Z is the number of protons, and each proton has a charge of plus E. And minus E is the charge of the electron. This is Q2, right? So electrostatic potential energy between two point charges placed at a distance r from each other is written in the following manner: K Q1 Q2 by R. That is the simplified understanding that I would want to give you. नहीं, R square कर देते हैं तो फिर वो force होता है. That is the electrostatic force. हाँ. Correct. Potential energy is just R raised to the power of 1. हाँ. So अब इसमें sign काफी क्रूशल हो जाएगा. ओजस, यू आर राइट टू पॉइंट आउट एंड हाईलाइट कि ये साइन लेना जरूरी है क्या? कांट बी वर्क विद मैग्नीट्यूड्स. दैट्स एन इंपॉर्टेंट ऑब्जर्वेशन कमिंग फ्रॉम ओजस. नाउ साइन बहुत इंपॉर्टेंट रहेगा, एंड गिव मी 5 minutes एंड आई विल ब्रिंग द इंपॉर्टेंस ऑफ साइन इन फ्रंट ऑफ यू. ठीक है? अब नोटिस करना यहाँ पर we'll substitute the results that we had derived for V and R. So substitute the results of V and R. What were the results? उसके लिए हमें एक बार लास्ट क्लास में जाना पड़ेगा. लास्ट क्लास में लाइक ये वाले जो रिजल्ट्स हमने निकाले थे, these ones, this and this, जो ये वेरिएबल्स के टर्म्स में थे, not the numerical ones. I would put the variable ones first. So if I put them, then what is the result that I'm getting? तो मैं डायरेक्टली यहाँ पे कर देता हूँ rather than going into duplicating that effort. We get 2 pi square m k square e raised to the power of 4 upon h square into z square by n square, and minus 4 pi square m k square e raised to the power of 4 upon h square into z square by n square. For those who are wondering, क्या बात है सर को ये एकदम like याद है? The answer is no. मुझे ये याद नहीं है. I am also looking into a reference and writing this up because I generally don't believe in mugging up a lot of information. So I myself don't know this, as in don't remember this, but if you ask me, I could have very well derived it in a minute or two for you. But that's also something which you will be able to do with the time. थोड़ा सा आपको derivation का practice हो जाएगा, तो it will be a piece of cake, as I said. Now, it is important to highlight something over here, that this is the kinetic energy and this is the potential energy ka term. Can you see that the two terms are very similar to each other? And once I combine them, once I write the net of it, I will come up with the answer minus 2 pi square m k square e raised to the power of 4 upon h square into z square by n square. Now, this is something which brings me to a very important result. ठीक है, यहाँ पे notice करना before I move on and substitute these constants ka values like I did in the previous cases, I would want to notice the similarity over here. And that similarity is something which you can understand in the following manner, that 2 times kinetic energy is equal to minus of potential energy in this case. Like if I multiply kinetic energy by 2, right, it will be equal to minus of potential energy. And this total energy term, then I can equate, it will be equal to the minus of kinetic energy, or I can write it as half of potential energy. Okay, just an important result for you to remember. Okay, sometimes this comes in handy. You will notice while we're doing questions. So this, now if I substitute the values of pi, mass of electron, electrostatic force constant, charge of electron, Planck constant, these are constants which I know the values of. And if I substitute them, then I get my answer as minus 13.6 z square by n square in the units of eV. That's electron volt. Okay, so this was the derivation of energy of electron in nth orbit. Now, there are two important notes with this result that I would want to highlight for each and every one of you. One is a normal note, like it will be relevant for everyone using this particular formula for any examination, be it medical ka examination, be it mains ka, be it advanced ka. But the other note that I'll be talking about is specifically for the advanced examination. ठीक है, so आप एक एक करके अब notice करना. So let me write down the first note. The first note is related with this negative sign. Okay, so this negative sign does not mean negative energy. Like there is nothing like negative energy. I'm sure that you have all your fancy dark energy stuff with you in your mind, but this does not mean that this is not some negative energy kind of thing. Okay, this negative sign signifies electrostatic attraction. Okay, it signifies the attractive force between electron and nucleus. That is what this negative sign does. Now, how does it do that? ठीक है, यहाँ पर आप notice करना. It's pretty simple to grasp it in a numerical manner. So if I talk about energy of electron in the first orbit of hydrogen atom, right? So I substitute the Z and N over here. So minus 13.6, hydrogen atom का Z 1 रहेगा और N भी 1 रहेगा. So I get minus 13.6 eV. This is the energy of electron in the first orbit. Now, for electron far, far away, okay, so it is as good as outside the atom. ठीक है, infinity मैंने यहाँ पर put किया हुआ है, like I'm saying n tends to infinity. That means like we are removing the electron. ठीक है, removal of electron or electron far away from nucleus. Then what can you say that the energy, like अगर denominator में, like यहाँ पर n denominator में this tends to infinity, then this value will tend to 0. ठीक है, so far, far away from the nucleus, when electron and nucleus are so far that they are hardly interacting, there is hardly any interaction between them, we assign the energy to be 0. And now अब आप notice करना, if we wish to remove this electron, right, then change in energy क्या होता है, right, removal of electron, the change in energy will, change is always written as final minus initial. I hope that has now like set into your brains that always follow this convention, that change is always final minus initial. What is final? 0, because it is far, far away from the nucleus, and initial was minus 13.6, right? So you get the answer as that the change in energy is plus 13.6 eV. And what does this signify? यहाँ पे notice करना, this signifies that this much amount of energy has to be supplied. Right? This is energy absorbed, that is work needs to be done to remove electron from atom. ठीक है, so I would need to supply this much energy so as to eject the electron out of the atom, and that is where the negative sign signifies that there is attractive force between electron and nucleus. हाँ, एक एक करके आपके डाउट्स भी हैंडल कर लेते हैं. हाँ, बोलो तौसीफ.
सर, तो ये जो एनर्जी ऑफ फर्स्ट एटम ऑफ हाइड्रोजन था,
फर्स्ट ऑर्बिट,
हाँ 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 सर, ये फर्स्ट ऑर्बिट था, ये हाईएस्ट इलेक्ट्रोस्टैटिक फोर्स था हाइड्रोजन के लिए.
हाँ, so we will be looking into the energy levels of the other orbits, but yes, to remove the electron from the first orbit we will require this much energy, which will be the highest.
ओके सर, तो और जो ये इन्फिनिटी था ये लोएस्ट है. ओके सर.
हाँ,
थैंक
right. हाँ, बोलो शर्विन.
Yes, sir. Sir, why didn't he keep the formula in positive only, sir? Means why did he give that negative sign? Means the
Right.
positive sign can also show the same result.
It wouldn't show the same result, but
Means that the calculation which you just did, sir, that plus 13.6 electron volt, it
हाँ,
would just come as minus 13.6, sir. So
हाँ,
it doesn't make much difference.
हाँ, नहीं नहीं, okay, ठीक है. So I was not willing to actually go into the physics part of it, but अब क्योंकि आपने पूछ लिया है तो चलो ठीक है, मैं आपको थोड़ा सा इसका फिजिक्स का एस्पेक्ट समझा देता हूँ. जब हम लोग let's say, let me go towards this side, when we have two charges with me, say q1 and q2, right, and these two charges, they are of say opposite sign, एक
Yes,
पॉजिटिव
sir.
है और एक नेगेटिव है. right? So we have attractive forces between them,
Yes, sir.
right? Now, if we were to separate them,
Yes, sir.
so we will have to do work, we will have to supply energy.
Yes, sir.
Okay, so this is one thing that we clearly understand. Okay, if there are two charges which are of same sign, then to bring them close, we will have to do work
Yes, sir.
because they will be repelling each other. Correct? So we understand this concept that like charges repel each other, opposite charges attract each other.
Yes, sir.
Correct? Now, अब notice करना that potential energy, electrostatic potential energy जब define करी जाती है, let's say ये इसका scale है, ठीक है? So what we understand is that if we have two charges which are of opposite sign, then we would want their potential energies to be in the negative region. If we have two charges of the same sign, we would want their potential energy in the positive.
Positively. Yes, sir.
And this zero potential energy is something that we have assigned. This is by convention. When r, that is the distance between them, that approaches infinity. Okay, when r approaches infinity, that is the charges are far, far away from each other, the potential energy is to be zero.
Yes, sir.
Okay, this is by convention. This is what we have decided. Potential energies are based on conventions. जैसे आपने gravitational potential energy के साथ में भी पढ़ा होगा ना, that we define certain reference. Say this is height 0. इसके ऊपर positive gravitational potential energy, इसके नीचे negative gravitational potential energy. इस तरीके से
Yes,
आप
sir.
करा होगा. तो उसी तरीके से
Okay, sir. So the nucleus is the positive charge and electron is the negative charge. So it will come in the negative region.
right. So अब in fact अगर मुझे उनको separate करना है, like I have to take them away from each other. ठीक है, r infinity को अप्रोच करना है, then I will be going from negative values to zero values. So that
Okay,
might
sir.
change क्या हो जाएगा, 0 minus minus something negative, and that becomes positive, which is a reflection of that energy is absorbed or energy has to be supplied.
Okay, sir. Yes, sir. Got it.
ठीक है.
Yes, sir.
Now I'm sure that some students would have been able to get this, okay, but I also at the same time understand that many students would not have been able to get this because this is, as I said, इसमें थोड़ा physics का background चाहिए रहता है. ठीक है, some students who would have been able to get this, it's really good, great, you guys are ahead in the curve. ठीक है, but I generally tend to skip this in the beginning part because some students don't get this idea of potential energy right away. तो अभी to simplify for everyone, ठीक है, यहाँ पर ध्यान से notice करना, to simplify for everyone, right, we had started with writing total energy as kinetic energy and potential energy, and the formula for potential energy, okay, that is being used is k q1 q2 by r, and we substitute the signs as it is. The nucleus was positively charged, the electron was negatively charged, so you put that right over here, and then you simplify the calculations and you get the results of energy of electrons. Now these energies of electrons, they come with a negative sign, and this negative sign does not mean any negative energy. Okay, it is just that it will simplify and understand, it will signify attractive force between electron and nucleus. Okay, and why is it so? This is, as I said, by convention. Okay, this is completely by convention because you might have this idea in your head ki what if we assume the other way around? The answer is you can. Okay, definitely you can. And if collectively each and every person in the world starts to think in that manner, then it becomes the new convention. Okay. However, we are not in the position right now to change conventions. So what we will do is we will go ahead with the conventions that have been established. And in this case, that negative sign, the convention that we have is it is signifying the attractive force between electron and nucleus. Okay. And we did a quick calculation of why that negative sign is important, so that we understand these changes. These changes in energy are going to be of really importance to us. Great. So this was one note as I was talking about. ठीक है. Second note, ठीक है, यहाँ पर अब आप notice करना, this is something which is strictly, as I said, for from advanced perspective. Now can you notice the result of the energy of electrons? How is it proportional to the mass of electron? It is coming out to be directly proportional. Correct? Now, अब notice करना, if I ask you a question and would want to know your thoughts on it. So there are two isotopes of hydrogen. In fact, there are three isotopes commonly known. So let's talk about the two. There is hydrogen and there is deuterium. What is the difference between the two? Like protonium and deuterium, right? What is the difference between the two? Correct, mass number. Now, do you think in this formula in front of you, does that difference feature? This is mass of electron, okay? So don't get confused with this as the mass of the nucleus. This is mass of the electron. Right, so this formula in front of you comes out to be same for these two isotopes, hydrogen and deuterium. However, experimentally, when the spectrum of hydrogen and deuterium were observed, there was difference between the two spectrums. Slight difference, small difference, but there was. ठीक है, क्या होता है spectrum? I'm sure that some of you are aware, some of you are not aware, but say this is some property. Okay? Or I would say, let me simplify this because of, let me simplify the potential energy levels or energy levels. Let me simplify this saying that energy levels of hydrogen and deuterium were slightly different. Although the Bohr's model, it didn't take that into account in the first attempt. So that is where I will like to introduce a small concept, and again pardon me for not getting into the derivations of it, because that derivation again requires knowledge of physics, knowledge of rotational motion to be specific. So यहाँ पर अब आप notice करना, how is this explained? ठीक है, give me a couple of minutes and we shall go through this. Okay, so let me bring in the note. experimental observation. Okay, so we have someone who would want to answer. Bolo Tripti.
Sir, I did not raise my hand for saying answer. I had a doubt.
Okay, okay, ठीक है. I thought that was because of that. Bolo. हाँ. अरे, you got unmute again. एक minute, let me unmute you. नहीं
Yes,
तृप्ति,
sir.
आपकी आवाज नहीं. हाँ, अभी आ रही है. बोलो.
Sir, the doubt was that you took the minus sign in the first calculation. I That's okay, but then in the last class, you didn't for force balance. You did not take the minus sign. You took directly mod y.
करेक्ट करेक्ट. सो यहाँ पर भी, ठीक है, यहाँ पर भी एक्चुअली द माइनस साइन इज इम्पोर्टेंट. ठीक है. And the reason why I didn't take that is because then I had to talk about vectors and talk about the fact that force is a vector and it has got direction. So the negative sign here, this would imply, okay, you have q1 charge, you have q2 charge, and if you have a negative sign of the force, that means that the force is of attractive nature along the line connecting the charges and towards each other. That would what the force would represent. So yahan par, let's say if I define this as the convention for force, that it's a vector quantity. If I decide this direction to be positive and this direction to be negative, right, then can you see the electrostatic force acting in the negative direction and the centrifugal force acting in the positive direction? Sorry, हाँ बोलो तृप्ति, समझ में आया?
Yes, sir. But then, sir, can you explain it again? I did not understand it clearly.
अच्छा अच्छा, ठीक है. So okay, the thing is, see, this is again a concept of physics, that when you learn in physics, there is a concept called as free body diagram.
Yes,
Okay.
sir.
And in that concept, what you do is you take your system, in this case it's an electron, okay,
Yes,
and you first decide sign convention around it. When discussing forces on it, you decide the sign convention around it, that along, say, x direction in a positive manner, we'll say that the force is positive. Along the left hand side, say, we will say the force is negative, or you could flip this also, like this is something up to
yes,
you. Up is positive, down is negative. You decide those direction conventions. Okay. Now you look into the results of the force that are being applied on that object. So in this case, the force of attraction, the electrostatic force of attraction, is acting towards the left hand side, and the centrifugal force was acting on the right hand side.
yes, sir.
ठीक है. So that is where यहाँ पर अब आप notice करना, ये जो negative sign है, this is featuring, or this is talking about the direction in which the force is acting. So it is going to be acting in a attractive manner towards each other. Had the nucleus been also negatively charged, right, then the force of or electrostatic force would be of repulsive nature, and it would have positive sign, and that would mean that it will be acting radially outwards.
Yes, sir.
Okay. So because I didn't want to get into those like nitty-gritties of sign convention in physics, that's why I was like, okay, chalo, let me just compare the magnitude of the two forces. They are
Okay.
acting in opposite direction, so I just compared their magnitude and went ahead with that.
Okay, sir. I understood.
Okay, good. Coming back, अब यहाँ पर आप notice करना the point that I was saying, experimental observation of spectrum of hydrogen and deuterium show slight difference in energy levels of electron around nucleus. Okay, so this is something which is explained by modifying the Bohr's model. So what is the modification? यहाँ पर notice करना, earlier what was thought was electron revolves around stationary nucleus. That was the observation, or that was the understanding, that nucleus is stationary and electron is revolving around it. The modified version that comes here is then both electron and nucleus revolve around their center of mass. Again, as I said, this is strictly point of view from the point of view of advanced. I am not sure if you guys are aware about this concept of center of mass. Okay, so इसमें what we are trying to say, or what is meant by this center of mass, let me just quickly like demonstrate that. So let's say you have a triangle, okay, hollow triangle, okay. Intuitively, can you replace this triangle by a point of the same mass? And if you would do so, then intuitively speaking, you would equilateral triangle hai, so you would choose to put the center of mass at this centroid या in center या circumcenter of this equilateral triangle. Correct. Right. So this is what, simply speaking, the concept of center of mass is. That the entire rigid solid object can be replaced by a single point and the entire mass concentrated at that point. Okay, so यहाँ पर भी on those intuitive lines notice करना. So you have nucleus and you have electron, right? अगर दोनों का मास m और m रहता है, सेम मास रहता है, तो सेंटर ऑफ मास कहां पर होगा? In between, if both were of the same mass. ठीक है. However, we understand that the mass of nucleus is much greater than the mass of electron. So this center of mass is much more closer to the nucleus as compared to that of as compared to electron, because nucleus ज़्यादा heavy है. And in this modified theory, what it says is that the nucleus is not stationary. In fact, the nucleus and electron together revolve around their center of mass. This is the modified version. Now, अब इसके पीछे की physics is much more tricky. It is not as simple as this. मतलब ये तो in fact काफी simple physics था. इसको हम लोग circular motion करके physics में पढ़ लेते हैं. That okay, centrifugal force and all calculate करना कैसे होता है. ठीक है. This is in fact a harder version of that. इसको हम लोग rotational mechanics chapter में पढ़ते हैं. Physics में आप लोग सीखोगे. You will study this concept of ऐसे rotation of two bodies around a center of mass. And in this, ठीक है, अब यहाँ से notice करना, I am putting forward the result. As a result of this modification, ठीक है, I'm directly using the result. The mass of electron is replaced by what we call as reduced mass. ठीक है, mass of electron is replaced by this term called as reduced mass. We represent it using the symbol mu in the formula of energy. What is this reduced mass? यहाँ पे notice करना, 1 upon reduced mass, it's a harmonic mean of mass of nucleus plus 1 upon mass of electron. इससे replace हो जाता है, ठीक है. इसके पीछे का derivation में मत जाना. This is something which you will not be able to derive right now, but it is an important concept to know. मतलब, in fact, this is, if you would read J.D. Lee, I'm sure, have you guys heard this or learned about this, heard this book before? J.D. Lee, it's a very, very important book for inorganic chemistry. Okay, this is not to be referred to right now. Okay, but this is something which is very, very important for inorganic chemistry. You are going to refer to it when you will be in class 11th and 12th. So वहीं से मैंने ये like pick किया है आप लोगों के लिए. So from the perspective of advanced, do understand and remember this modification, that because of the difference in the energy levels observed for isotopes, we understand that the nucleus and its mass also plays an important role. And this is what causes the difference. Right? This mass of nucleus is now different for the isotopes. This is different for plutonium and deuterium. And this is what causes the change in the energy levels. ठीक है? नहीं, reduced mass है तौसीफ, आप increased mass नहीं है. In fact, if you will notice, this comes out to be like this concept of reduced mass is going to be something which you can say. So यहाँ से आप mu निकालोगे ना, like if you would compute, ये mu कैसा आ जाएगा? Mass of electron times mass of nucleus upon mass of nucleus plus mass of electron. So can you see that this term is less than 1? Like that's why it's called reduced mass. ठीक है, not increased mass. वो I think आपको शायद गलत एक perspective आया होगा यहाँ पे. Anyways, so this is something which I would want you to remember from advanced perspective. Okay, now let's come back to the normal concepts which we had studied some time back. Energy of electron in the so you just need to replace this mass of electron. So यहाँ पर ये जो formula था आपका energy का, इसमें all you need to do is replace this m term with mu. ठीक है, all right. Now ये थोड़ा सा heavy stuff था. Let's come back to the regular normal calculations of Bohr's model. So यहाँ पर notice करना, radius diagram of hydrogen atom, and on the same side I will put forward the energy diagram of hydrogen atom. Now notice करना, R was proportional to n square by z. Now what that meant was that let's say if this was the nucleus and this was the radius of the first orbit, if this was x, then what will be the radius of the second orbit? It will be 4x. Right? What about the radius of the third orbit? It will be 9x, and so on and so forth. Correct? So what you can conclude from here is, as we move away from the nucleus, what about the radius of the orbit? Radius of the orbit increase. There's no surprise in that. But the noticeable thing is, यहाँ पर notice करना gap. Which gap are we talking about? The distance gap. ठीक है, gap between successive orbits, that also increases. ठीक है, right? यहाँ पर gap between first and second was 3x, second and third would be 5x, and so on. Consecutive, successive मतलब consecutive orbits के बीच का. ठीक है, all right. Now अब यही चीज आप एनर्जी के पर्सपेक्टिव से नोटिस करना. We just derived the result of energy of orbits, and we found out that energy is proportional to, or in fact, let me write the entire formula, minus 13.6 into z square by n square in the units of EV. So now, अब आप notice करना एनर्जी डायग्राम किस तरीके से ड्रॉ किया जाता है. सो लेट्स से दिस इज n equal to 1, right? Let me in fact draw proper line. Okay, so this is n equal to 1 and this is minus 13.6 eV in terms of its energy. If I put n equal to 2, what will be the energy? थोड़ा सा मैथ्स लगेगा. So if you put n equal to 2, then the energy level will come out to be minus 3.4 eV. Right? The gap between the two here will be how much? 10.2 eV. Put n equal to 3. And you will get this as minus 1.5 eV, 1.5, 1.51 ऐसा कुछ आ जाएगा. Right? So can you notice the gap diminishing, right? How much will this be? This will be around 1.9 EV. Now you put n equal to 4, this gap further diminishes. Okay, let me actually bring these more lower. This will be n equal to 4 and this will be minus 0.85 EV. Correct. So the gap further decreases, and like similarly you can kind of say that n approaches infinity, this approaches 0 EV. Right. So what you can conclude from here is, on the same lines, as we move away from the nucleus, what is happening with the energy levels? Energy levels increase. Like this is increasing with sign sochna hai. Minus 13.6 is lower energy. Okay, minus 3.4 is higher energy. Okay, please think of it in terms of sign. And what about gap? This time the gap is not in terms of distance. This is with respect to energy. Right. So what is happening to the energy gap between successive orbits? That gap is decreasing. Right. So I hope this is something which you are able to grasp. हाँ. Okay, so Shravin, आपका doubt था थोड़ा time पहले. I'm sorry, I was not able to pick that up.
Yes, sir. So
हाँ,
I have three doubts.
बोलो बोलो.
So, can you show that modification once?
Yes, yes.
Yes, sir. So, according to this, sir, the center of mass is just beside that nucleus, right?
हाँ,
But, sir,
nucleus is more heavy, much more heavy than that of electron.
yes, sir. But according to Rutherford, sir, all the mass is almost concentrated at the nucleus. So, the center of mass should be inside the nucleus, right?
नहीं नहीं, okay. So see, what we are considering over here is nucleus and electron both as point masses.
Okay, sir.
Okay, so from Bohr's model perspective, we are considering them to be point masses. And then when we talk about their attractive force and their revolutions, so this is the modified version that we come across as the system of nucleus and electron revolving around the combined center of mass, and that is quite close to the nucleus, right? But we'll not say that it is inside the nucleus because we are talking about nucleus as the point mass over here.
Okay, sir. And sir, if so, the electron is performing different revolutions around the nucleus and around the center of mass.
No,
But
no,
sir,
no.
how is
It is now around the center of mass only.
so
Not
say so the around the nucleus concept is now not there?
no, no, that got replaced. Like they together are revolving, but they are revolving around the center of mass.
Okay, sir. Yes, sir, got it. And sir, my third doubt was that, sir, in that energy gap, sir, that diagram which you showed just now,
Mm-hmm.
so that at a point of time, sir, the difference between the two shells will almost become means approximately will be zero. So does this mean, sir, that the two shells will have the same energy?
Very close. Like so for practical purposes, जब हम लोग एनर्जी लेवल्स का डिस्कशन करेंगे तो आप नोटिस करोगे कि अराउंड 5-6 तक जाने के बाद में, like we say that the remaining shells, they are in terms of energy, they are like very,
Zero only.
हाँ, तो उनके बीच का गैप इज नेग्लिजिबल.
Okay, says got it.
हाँ, बोलो तृप्ति.
Yes, sir. So minus sign indicates that there is a force of attraction. So,
Correct.
sir, why are we thinking over here that E is increasing, and why are we thinking it with sign convention? Because the force of attraction is decreasing, no?
हाँ हाँ, force of attraction is decreasing. करेक्ट. बट जो पोटेंशियल एनर्जी है हमने वो नेगेटिव के टर्म्स में डिस्क्राइब करा है. करेक्ट. अब this will make sense to you. Let's say if I was to remove the electron from n equal to 1 to far away, how much energy would I require? 13.6 ev. And if I was to remove the electron from n equal to 2 to far away, then how much would be the energy required? 3.4 ev. Correct. Now, in which case more energy is required?
So, in the first case,
And why would that be? Because it is attracted more by the nucleus. It is closer to the nucleus.
sir, so it is with respect to the potential energy that how much energy is required to remove and not to attract.
Correct.
Okay, sir. I understood.
बोलो प्रकाश.
सर इन द लास्ट स्लाइड सर आपने एक फॉर्मूला लिखा था सर, जैसे 2k इज इक्वल टू माइनस पीई.
हाँ हाँ,
सर ये सब मतलब मेरे को समझा नहीं वो कैसे
मैं
आया.
अभी जस्ट एक नहीं वो तो जस्ट यहाँ पे एक्सप्रेशन देखो ना, ये कितना सिमिलर है. मतलब लाइक दिस एंटायर एक्सप्रेशन एंड दिस एक्सप्रेशन इज द सेम एक्सप्रेशन.
यस सर.
सब्स्टिट्यूट v over here, मैंने सब्स्टिट्यूट r over here.
यस सर. यस सर.
So I get the same looking expressions with small difference between them, and that is what I wanted you to notice over here.
ओके सर. सो दे हैव डिराइव्ड दिस ना.
हाँ, this got derived.
ओके सर. ओके सर, गॉट इट. थैंक यू सर.
ठीक है, अभी मैं इस पे एक दो क्वेश्चंस भी कराऊंगा आपको. हाँ, बोलो तौसीफ.
So can I ask you the doubt afterwards? I forgot the doubt now.
ठीक है, आप लिख लिया करो. बोलो गौरव.
Sir, I had a similar doubt about the center of mass. I wanted to ask that when we consider over here the nucleus to be a point charge or a point mass, but in in real life, like or in practical life, we consider the nucleus to be a collection of protons and neutrons, right?
Correct.
Sir, so then according to that, if we are considering it not as a point mass and as a collection of masses, then it is possible that the center of mass is inside the nucleus, and the nucleus like not completely at the center of the nucleus, but a bit inside the nucleus.
So okay, बिल्कुल आपने सही डायरेक्शन में सोचा है गौरव. Now understand that we are going in a chronological perspective, wherein we are trying to understand the way in which the model or the structure of atom got evolved, right? So Bohr's model isn't the modern theory, isn't the final version of what we understand as the structure of atom. Okay, there are theories which are you can say evolved version. I would not say Bohr's model is incorrect. I would say Bohr's model was incomplete. And then there are these theories that came afterwards, which made you know which were I would say more accurate. They made better progress in terms of understanding the structure of atom. तो उसी तरीके से you are right to point out that like the center of mass, assuming point mass, might not be a correct idea, right? So that's absolutely fine. You are right in assuming that okay, if I don't consider this point mass, then I might be able to do a more accurate version of what the structure of atom would be. However, at that point in time when Bohr's model was evolving, these experimental observations were poking hole in Bohr's model, and as a result, there were certain modifications that got done so as to overcome those and explain those experimental observations. Okay? In fact, there is one more which we don't really teach because it becomes more complicated. There is one more modification that happens to the Bohr's model, in which instead of the circular orbit, there are elliptical orbits. That is called as Bohr-Sommerfeld model.
So then the center of mass becomes the center of the ellipse and the nucleus is at the two foci. It
नहीं उसके पीछे
rotates.
का नहीं उसके पीछे का भी अलग कॉन्सेप्ट है. सो इट्स नॉट जस्ट बेस्ड ऑन दिस सेंटर ऑफ मास कॉन्सेप्ट. उसके पीछे like the understanding was because the energy of orbits was coming to be slightly different when observed under higher resolution experiments. That it was not कि एक particular energy level था, there were some nearby energy levels. So instead of observing one circular orbit, they were like there can be multiple ellipse corresponding to a close by energy level, and all those modifications got done. But as I said, that these are the ways in which the evolution of structure of atom got done. So you
Sir,
have
also one last question.
हाँ,
I understood what you said right now.
हाँ,
Sir, the Bohr's model, it was only valid for a single electron atom, right?
correct,
Sir, so are these energy levels also valid for a single electron atom?
correct.
And even after this modification, we can use it only for a single electron atom, right?
हाँ. Just give me one moment. Just give me one moment. Sorry, I had to take that call. Anyways, हाँ, तुम्हारा डाउट क्लियर हुआ गौरव?
Yes, sir, about that. And yes, sir, yes, understood. Sir, so and this center of mass one, the concept which we use, the modification, that is valid for all the atoms, right?
हाँ, it is valid for all the atoms. इसका origin was primarily to explain the difference between the isotopes.
Okay, sir.
हाँ, बोलो आरवी.
हाँ सर, जैसे जैसे हम लोग अलग मतलब आगे वाले ऑर्बिट्स में जाएंगे, फर्स्ट ऑर्बिट में सबसे कम एनर्जी होता है और आगे वाले में सबसे ज्यादा होता है.
हाँ, we will see.
और साइन को कंसीडर किया तो, और अगर नहीं किया मतलब अगर अट्रैक्टिव फोर्स देखा तो फर्स्ट ऑर्बिट का सबसे ज्यादा होता है और उसके बाद वालों का कम होता है.
Correct.
ओके सर. और सर इसके बाद वो बाल्मर पास्कल सीरीज आने वाली है, ब्रैकलेस सीरीज.
हाँ. We are going to talk about that is as part of the atomic spectrum.
ओके सर.
हाँ, बोलो वेदांत.
So when you're telling us about the energy levels for different shells, you told us that the potential energy is negative when it's attractive and positive when it's resistive, correct? So
Sorry, I missed that. Can you repeat, Vedant?
so when you were telling us about the energy levels, you told us that there's a point zero where there is no resistive or attractive force. Then the potential energy is negative when it's attractive and positive when it's resistive.
नहीं, अभी आप देखो यहाँ पर we have electron and nucleus, right? They have an attractive interaction between each other.
Yes, sir.
And that is why the potential energies, in fact, the total energy is coming with a negative sign.
So, but since the energy is increasing, can we say that there's a resistive force that's developing between the electron and the nucleus?
No. You will say that attractive force is decreasing. That's it. No repulsive force.
Thank you.
हाँ, बोलो ज्योत्सना।
Sorry.
अच्छा, आपने गलती से हैंड रेज किया था। ओके, ठीक है। सो नाउ लेट मी आस्क यू सम क्वेश्चंस बेस्ड ऑन दिस। ठीक है, इन द मीन टाइम आप लोग और भी डाउट पूछ सकते हो, आई डोंट माइंड, बट थोड़ा प्रोग्रेस करते जाएंगे साथ साथ में। ऑलराइट, लेट मी नो दिस क्वेश्चन का आंसर, एंड इन दिस आई विल rewrite the formulas for you. Total energy was equal to minus 13.6 z square by n square. Kinetic energy was minus of total energy, and another formula was potential energy is twice of total energy. Right? These are the formulas that I'm going to be using, and based on this give me the answer. Bolo Sharvin.
Yes, sir. So that energy levels, so that minus 13.6 EV, that all energies are the potential energies.
No, that's the total energy.
Okay, sir.
हाँ, इसमें केयरलेस मिस्टेक नहीं करना है, ठीक है। मेनी टाइम स्टूडेंट्स मेक अ केयरलेस मिस्टेक इन दिस, so that is where I would want you to take note. All right. अभी तक किस किसने सही दिया है? लेट मी टेल यू। क्षितिज, अनवी, राजदीप, गिरीश, आदर्श एंड अयाति हैव गिवन द करेक्ट आंसर। बाकी सबका गलत है। अच्छा हाँ, बाकी अब और देने स्टार्ट किए हैं। आरिश, मिहिर, तौसीफ हैव आल्सो नाउ गिवन द करेक्ट आंसर। ठीक है, देखो यहां पर आप इनिशियल क्या दिया हुआ है? काइनेटिक एनर्जी इज x, राइट। इंप्लाइज पोटेंशियल एनर्जी कितना हो जाएगा? -2x, राइट। यहां से रिलेशनशिप अपने को याद है। ओके, फाइनल काइनेटिक एनर्जी दिया हुआ है कितना? x/4, तो इंप्लाइज फाइनल पोटेंशियल एनर्जी कितना हो जाएगा? -2 times that. So now change is always final minus initial. ठीक है, तो यहाँ पर change in potential energy delta PE, that is what is being asked in the question. The final is -x/2 and the initial is -2x, and hence you get the answer as +3x/2, which means A option is the correct answer. ठीक है, आप लोग नोटिस कर लो एक बार किसने कहां पर क्या केयरलेस मिस्टेक करी। डू रिमेंबर, ठीक है। सो ऑप्शन ए इज द करेक्ट आंसर। ठीक है। हाँ, ठीक है। टोटल एनर्जी का ही कॉन्सेप्ट है जो कि हम यूज में ले रहे हैं। to help understand that how the energy level of electrons change. ठीक है, एक और क्वेश्चन मैं आप लोगों को कराता हूँ. ठीक है, यहाँ पर अब आप try and answer me this question. Determine the minimum frequency of photon okay, in fact rather than frequency let me ask wavelength. Determine the maximum wavelength of photon required to eject electron out of hydrogen atom. फटाफट निकाल के बताओ. भूल तो नहीं गए आप लोग? लाइक बोर्स मॉडल चल रहा है तो आप लोग क्वांटम थ्योरी ऑफ लाइट भूल गए? हाँ नहीं, नेगेटिव में नहीं आएगा आंसर गिरीश. अगेन आप यहाँ पे नोटिस करो, अभी इलेक्ट्रॉन n इक्वल टू 1 में है और यहाँ से आपको कहाँ निकालना है? बाहर निकालना है, राइट? सो यहाँ पर एनर्जी कितना है? -13.6 eV, राइट? एंड यहाँ पर एनर्जी would tend to 0, right? So what is the change? This is energy final minus energy initial, and this change is what will be done by a photon, correct? So यहाँ पर 12400 upon lambda in angstrom, because I am doing calculations in terms of EV, so I will use this formula 0 minus 13.6 EV. So I'll get my answer of the wavelength, ठीक है, in the units of angstrom. तो रफली कितना आ रहा है ये? अराउंड 911 एंगस्ट्रॉम आ रहा है, ठीक है. ऑप्शंस थोड़े दूर दूर रहेंगे तो ऑफ कोर्स यू कुड यूज द अप्रोक्सीमेशन एंड आंसर समथिंग क्लोज टू 900. हाँ हाँ शर्विन, करेक्ट. हाँ बोलो ईशान.
सर वो 12,400 के बाद वो कैसे आया?
ये वाला कैसे आया? ये hc बाय लैम्डा को सिंपलीफाई करते ना अपन.
नहीं सर, 12,400 के बाद जो -13.6.
ये फाइनल एनर्जी है 0.
यस.
और ये इनिशियल एनर्जी है.
यस इनिशियल. ओके. हाँ ओके सर.
ठीक है, ऑलराइट. हाँ बोलो प्रकाश.
Sir, so we can say that the X-ray can eject an electron from the hydrogen atom now.
Yeah, you can.
Sir, so if an hydrogen gas is placed in a container and X-ray is passed, so it will ionize the gas now.
It can, yes.
Okay, sir. Thank you, sir.
Another question. Fatafat. This I think everyone should be able to do now. हाँ, now I can see most of you are able to do it now. Correct, n equal to 1 से n equal to 2 जाना है, and this is what excitation is, right? So this was minus 13.6 EV and this was minus 3.4 EV. Abhi just I had calculated some time back for you, right? So this delta E was coming out to be 10.2 EV, correct? Right, minus 3.4 minus 13.6. So that was 10.2 EV. And this is what you could have written as the energy of photon. That is 12400 upon lambda in angstrom. And as a result, you will get the answer around 1215 angstrom. Okay, close to it. Okay. All right. Okay. एक और question try करेंगे. And this time it will be something based on those proportionalities that we had studied in the last class. All right. ठीक है, ये वाला क्वेश्चन ट्राई करो. एक मिनट, सॉरी. Try this question now. हाँ, right Kshitij, right Aravir, correct, correct Ishan, हाँ, right Gaurav, right Satvik, Jyotsana, मीर आपका भी correct है, good. ठीक है, so इसमें the catch is that you need to take the difference, as in make sure that total energy के बारे में आप आंसर कर रहे हो. Correct. A option is the answer. So notice करना है यहाँ पर kinetic energy was proportional to z square by n square, and that is the proportionality that is being asked. So kinetic energy in case A upon kinetic energy in case B will be z square by n square in case A upon z square by n square in case B. ठीक है. So in the first case, kinetic energy of the electron in the fourth orbit of hydrogen. So fourth orbit of hydrogen and first orbit of Li2 plus. First orbit of Li2 plus. So this will be, यहाँ पर notice करना 1 square upon 4 का square divided by this will be Z of lithium would be 3 का square upon N will be 1 का square. So you will get that kinetic energy of the first orbit of lithium 2 plus is coming out to be 144 times the kinetic energy of fourth orbit of hydrogen. Okay, but what is being asked is total energy, so don't forget that as the last step, since total energy is negative of the kinetic energy, right? So what are we getting over here? That total energy of the first orbit of Li2 plus will be minus 144 times this epsilon symbol or whatever this euro ka symbol is. All right. ठीक है. Now बेसिक क्वेश्चंस आपको समझ में आ गए हैं दैट हम किस तरीके से आंसर कर रहे हैं regarding Bohr's model of atom. However, there are certain terms which are specifically used in the Bohr's model of atom that are sometimes included in questions, and knowledge of those terms is crucial for you to be able to understand and comprehend the question, and then as a result articulate your answer in a fast manner. So notice karna, there are these some terms associated for single electron system particularly, and in fact for this case let me save some time. So I'm just copying some piece of information from one of the previous batches, and that will just help you save some time. Okay, इधर तो नहीं है. Just give me a moment. हाँ, correct. So these are some theoretical terms. ठीक है. I will be sharing the notes with you, so don't worry about the fact that sir हम copy नहीं कर पाए, but I just wanted to cover some part. थोड़ा सा doubts में क्या time फटाफट चला जाता है. All right. So यहाँ पर अब आप notice करना that we are going to talk about some terms for a single electron system. एक एक करके चलते हैं थोड़ा fast. The first term will be ground state. What is ground state? It is the lowest energy state, and in this case, in single electron system, it will be simply n equal to 1. ठीक है. Excited state. What is meant by excited state? Energy levels other than ground state. The higher energy levels, they will be called as excited state. However, यहाँ पर एक nomenclature रहेगा जिसको आप notice करना. That will be important for you to remember in questions. So in single electron system, second orbit, like first orbit को तो हमने क्या बोल दिया? Ground state. Second orbit will be called as first excited state. Third orbit will be called as second excited state, and so on and so forth. The nth orbit will be called as n minus 1th excited state, or n plus 1th orbit will be called as nth excited state. Okay. Then we come across this term called as ionization energy, or binding energy, or ionization potential. Now this ionization potential was something of an older term. अभी of late इसका use बहुत ही कम रहता है. ठीक है. More often we come across ionization energy or binding energy as a term. Now what is the definition of this? It is the minimum amount of energy required to take electron from ground state, that is n equal to 1 to n equal to infinity, right? And we just did certain calculations based on that. So for hydrogen atom, if I was to ask you what will be the ionization energy, you would just simply put in the energy levels of the first and the like far away, and you will get that answer. Okay. Oops, sorry. Right. Now notice karna, ionization energy of a particular state, that is also a term which is sometimes used. In general, अगर कुछ नहीं बोला जा रहा है, ठीक है, if they don't use this term, सिर्फ इतना बोला जा रहा है आयनाइजेशन एनर्जी ऑफ से Li2 plus ion. If that is being told, they are not using some particular state. Then what it's meant is that you have to take the electron from ground state to far away. Okay? But if in certain question they sometimes specify that ionization energy of a particular state, for example ionization energy of second orbit or first excited state of Li2 plus is, if that is kind of being asked. So what it means is that the minimum energy required to take the electron from that state, जो भी given state है, to n equal to infinity, right? So can you compute this value for me quickly? What will be the ionization energy of the second orbit of Li2 plus? हाँ, correct Kshitij, but with a small गड़बड़ that you made with the sign. नोटिस करना उसमें आपने क्या गड़बड़ करी. हाँ, मिहिर आपने भी वही साइन की गड़बड़ कर दी है. अनिर्वन करेक्ट आंसर. शर्विन करेक्ट आंसर. बाकी जनता नहीं, दैट इज नॉट द करेक्ट आंसर. यू गाइस वर्क ऑन इट. हाँ, आकाश करेक्ट. तृप्ति करेक्ट. आप लोग देखो कहाँ पे गड़बड़ हो रही है. n equal to 2 से n equal to infinity जाना ना. So that's it. 30.6 is the correct answer. Z square by n square का फॉर्मूला यूज करना है. हाँ, ठीक है. I hope you guys are able to get a grip on this. Just follow the sign convention. है simply formula. ठीक है, ये समझ में आया. Is anyone uncomfortable with this question still? ठीक है. Pardon my writing again. Like these were those earlier days when I was getting used to the writing on these tablets and all. As in, I've still not been able to master them. But उस टाइम तो बहुत ही गंदी हैंडराइटिंग थी. अभी फिर भी थोड़ा बेटर हो गया है. All right. हाँ, I know Sharvin. Same here. ठीक है, एक नेक्स्ट टर्म आप यहाँ पर देखो. That is called as excitation energy. Now, can you guess before I start giving you the definition of what excitation energy would be? हाँ, बोलो ईशान.
Sir, the energy to jump from one orbit to the other.
ठीक है, थोड़ा सा और स्पेसिफिक होंगे इसमें तो आई थिंक दैट विल मेक मोर सेंस. इसमें थोड़ा स्पेसिफिक जाएंगे तो यहाँ पर आप नोटिस करना, मिनिमम एनर्जी रिक्वायर्ड टू एक्साइट इलेक्ट्रॉन फ्रॉम ग्राउंड स्टेट to some higher state is called excitation energy of that state. ठीक है, खूब सारी इंग्लिश हो गई, तो एक बार सिंप्लीफाई करते हैं इसको. Excitation energy of third state of hydrogen atom. What will this mean? तो अब आप वापस से डेफिनेशन को रीड करो. मिनिमम एनर्जी required to excite electron from ground state to some higher state is called the excitation energy of that state. यानी कि we will have to excite the electron from n equal to 1 to n equal to 3 in hydrogen atom, and that energy which is required is going to be the excitation energy of the third state of hydrogen atom. ठीक है, हाँ बोलो गौरव.
Sir, I wanted to ask in terms of this excitation energy only. Sir, when we say that the excitation energy, like I remember somebody asking that when there is more than the required energy, what will happen? And you said it won't jump. Sir, so is it possible that when a photon is applied of let's say in case of hydrogen atom 10.2 ev from the first to the second state,
Correct.
or I mean the ground state to the first excited state, sir, so then if I let's say there's a photon which supplies energy of 10.5 ev, then will the will the electron jump from first to second and gain some more kinetic energy, or will it not jump at all?
No, it won't jump at all.
Sir, so why does it not have more kinetic energy imparted and go into the second orbit?
You're right, because see, the electron is governed by the nucleus when, as long as it is inside the atom. So nucleus has decided that only certain quantized energy levels can be there, and corresponding to those energy levels there can be certain kinetic energy, there can be certain potential energy, there can be certain angular momentum, and those energy levels are going to be present.
Okay, so then except the quantized energy, or perfectly how much ever energy is required, we can't use an photon.
So that is what the concept of quantization happened at an atomic scale. That ऐसा नहीं है that energy is continuous कि अभी electron like ऐसे around say in this r radius का orbit move कर रहा है, and आपने थोड़ा energy provide कर दिया तो थोड़ा खिसक गया, थोड़ा सा higher energy level पे move करने लग गया. Like it's not that there is a continuous range of energy in which the
Yes, sir.
electron can be
Yes,
present.
understood.
There are these quantized energy levels which are governed by the concepts of quantum physics that are only allowed.
Yes, sir.
And that is where when, let's say, a photon which is not corresponding to the gap between these energy levels, then that photon isn't something that is going to be interacting with the electron. हाँ, अगर ionize करना है, like अगर आपको न्यूक्लियस के इन्फ्लुएंस से बाहर ही ले जाना है, ठीक है, तो आप कोई सा भी हायर एनर्जी का फोटोन अप्लाई कर सकते हो. मतलब 13.6 eV से ज्यादा कोई सा भी फोटोन आप अप्लाई करोगे, यहाँ पर ऐड करोगे, अब्सॉर्ब करोगे, तो दैट कैन इंटरेक्ट विद इलेक्ट्रॉन बिकॉज नाउ इट takes the electron out of the atom away from the influence of nucleus, and then that's a free electron. So that free electron can then possess kinetic energy also. ठीक है, then it is not corresponding to those quantized energy levels. समझ में आया?
Yes, sir. Understood.
ठीक है, मैं लिखवाऊंगा आगे, ये नोट के फॉर्म में भी मैं लिखवाऊंगा. अभी तक वी हैव बीन जस्ट टॉकिंग अबाउट इट. I will again make this as a note. हाँ Sherwin, I have included that as part of the notes also. तो एक बार वहाँ पर आ जान दो, then I'll re-explain. Okay. अब notice करना with this definition of excitation energy. ठीक है, ये जो definition थी, इसके साथ में एक nomenclature associate हो जाता है. किस तरीके से? Like one would be very simple for you to understand that I can write excitation energy of third state of hydrogen atom I can write it as excitation energy of the second excited state of hydrogen atom, because we just understood the definition of excited state. So n equal to 3 means second excited state, right? So this is plain simple obvious. ठीक है, third state मतलब third orbit, second excited state, ठीक है, the word excited should be used. Second excited state would mean the third orbit. ठीक है, हाँ बोलो तौसीफ.
Sir, I have two doubts. First, can you explain the excitation energy again?
So excitation energy आप notice करो that यहाँ पर, let me put it in a perspective of a diagram. Nucleus के around energy levels.
Yes sir.
ठीक है. Now single electron system जो रहेगा उसमें naturally electron will be found in n equal to 1, lowest energy orbit, lowest energy state.
Yes sir.
Now when you supply photons to this atom, then they can either ionize this electron or they can excite this electron.
Yes sir.
ठीक है.
Yes
तो
sir.
इसके जस्ट पहले हमने आयोनाइजेशन एनर्जी का डिस्कशन करा था. That ionization energy, that will be the minimum energy required to
yes sir, to eject electron.
हाँ, eject the electron. अब उसके बाद में मैं एक्साइटेशन एनर्जी का डिस्कशन कर रहा हूँ, in which I am talking about that if the electron still stays in the influence of nucleus, it is not out of the influence of nucleus, it is going or jumping to higher energy levels, then
Yes sir.
what would be the energy required to do so? So that is being called as excitation energy. Now, as you can see that going from n equal to 1 to n equal to 2, n equal to 3, n equal to 4, right? Those are, ठीक है, यहाँ पर in fact I should not use the word minimum because there is no range as such. I should rather use the word simply just energy. So n equal to 1 से n equal to 2 जाने के लिए जो energy लगेगी, that will be called as the excitation energy of the second orbit.
Second orbit. Yes sir.
n equal to 1 से n equal to 3 जाने की जो energy लगेगी, that will be called as the excitation energy of the
Third
orbit and so on so forth.
सर तो ये जो थर्ड स्टेट यूज किया है इन लोगों ने, ये एक्चुअली थर्ड ऑर्बिट है.
Third orbit. Unless and until excited word is being used, just consider state, shell, orbit to be all synonymous.
हाँ सर, और उसके बाद ये बोर्स मॉडल पर जाइए ना, तो बोर्स मॉडल में डाउट है.
किस पर?
बोर्स मॉडल का जो सेंटर ऑफ मास वाला कॉन्सेप्ट था,
उस पे थोड़ी देर बाद आते हैं, रुक जाओ, अभी थोड़ा ऑफ टॉपिक चले जाएंगे फिर अभी. ऑल राइट. हाँ, सो एज आई वाज टॉकिंग अबाउट, ठीक है, द नोमेनक्लेचर, यहाँ पर एक्साइटेशन ऑफ थर्ड स्टेट ऑफ हाइड्रोजन एटम, और इट कैन बी रिटन एज एक्साइटेशन एनर्जी ऑफ सेकंड एक्साइटेड स्टेट ऑफ हाइड्रोजन एटम. ठीक है, और इट कैन ऑल्सो बी रिटन एज सेकंड एक्साइटेशन एनर्जी ऑफ हाइड्रोजन एटम. ठीक है, नोटिस करना ये नोमेनक्लेचर कहाँ से आ रहा है. तो अभी जस्ट हम लोग बात कर रहे थे कि इलेक्ट्रॉन n इक्वल टू 1 में प्रेजेंट रहेगा, तो उसका एक्साइटेशन 1 से 2 भी हो सकता है, 1 से 3 भी हो सकता है, 1 से 4 भी हो सकता है. तो these are if put in an order, so we call this as first excitation energy, second excitation energy, third excitation energy, and so on and so forth. So hence the one which I was talking about, excitation energy of the third state, right, यानी कि n equal to 1 से n equal to 3, so that can also be given the name second excitation energy. Okay, so this is one I would say theoretical point, more of a nomenclature thing that is sometimes put in questions, right? So ये जैसे first excitation energy है, इसको हम लोग क्या बोल सकते हैं, excitation energy of the second orbit और excitation energy of the first excited state, right? This first excitation energy, अगर n equal to 1 से n equal to 3 जा रहा है, तो उसको हम लोग क्या बोल सकते हैं, excitation energy of third state or excitation energy of second excited state, right? Or just second excitation energy, and so on so forth. ठीक है, हाँ. So first excitation energy is n equal to 1 to n equal to 2. Second excitation energy is n equal to 1 to n equal to 3. ठीक है, नोटिस करना ये सब सिंगल इलेक्ट्रॉन सिस्टम्स के लिए ही है, these terms. So these terms are something which I honestly find them to be just unnecessary extra piece of information. बिकॉज कॉन्सेप्ट समझ में आ गया है, तो उसमें क्यों जबरदस्ती ये सब टर्म्स इंट्रोड्यूस करना. बट अनफॉर्चुनेटली like when you are going to appear for examinations, when you are going to come across questions, तो उनमें ये terms introduce करे हुए हैं. Like they just unnecessarily increase the complexity, and I can completely empathize with you guys on that. अब है तो लेकिन पढ़ लेते हैं, ठीक है. आई अंडरस्टैंड नोमेनक्लेचर कई जगह पर इंपॉर्टेंट है, समझना चाहिए, बट यहाँ पर इट वाज अननेसेसरी. बट पता नहीं क्यों डाल दिया है, ठीक है. सो ये एक्साइटेशन एनर्जी टर्म समझ में आया आपको? कैन आई आस्क यू कपल ऑफ क्वेश्चंस बेस्ड ऑन दिस नाउ, बेस्ड ऑन दीज टर्म्स? ऑल राइट, चलो लेट्स ट्राई सम क्वेश्चंस. ठीक है, let's try this question itself. All right. ठीक है, let me know your answer to this question. And बीच में if you want to scroll up and down and kind of remember what the definition was, then you can just ask me. देखो तौसीफ शर्विन, आपने केयरलेस मिस्टेक कर दी है. वही नहीं करनी थी. हाँ बोलो सूर्या. हाँ बोलो गौरव.
Sir, I had a question. When we say electrons are excited in a single electron system, does it not happen in multi-electron systems, like more than one?
No, it does. It does. But
It does, right? Sir, so let's say that if we have two electrons in the first shell and we have a noble gas arrangement, sir, so if we are trying to excite an electron from the first orbit, where does it go? Because in the second orbit, it all 8 of them are have occupied the second orbit, right?
नहीं मैं बात करूंगा, मतलब वी आर, जब मैं ये लाइक एसपीडीएफ कॉन्फ़िगरेशन के बारे में बात करूंगा, फिर हम लोग मल्टी इलेक्ट्रॉन में लाइक ग्राउंड स्टेट या फर्स्ट एक्साइटेड स्टेट के बारे में बात करते हैं.
Okay,
अभी
sir.
इन बोर्स मॉडल इट वोंट मेक मच सेंस. तो एक बार जब मॉडर्न कॉन्फ़िगरेशन पे आ जाएंगे तब उसके हिसाब से फिर बात कर लेंगे.
Sir, so is it something like we define energy levels between the first and second orbit?
Not really. We will be like going into the details of these energy levels, and what we will understand is that these energy levels, like that Bohr's model gave us, like these are, you can say, at a I should say higher level.
It's okay, sir, if like.
And then if we zoom into it, like let's say if you had a new way of looking at the energy levels, okay, and then what we find is that instead of like one energy level, there are multiple closely spaced energy levels.
Oh, okay, sir, understood.
So we are going to come to that, but in some time. तो इसका करेक्ट आंसर ऑप्शन ए रहेगा, ठीक है. फॉर दोज हु हैव got the answer, great. For those who haven't, then you guys have made a careless mistake. So notice karna, what was that you made a mistake about? The potential energy is given to you as minus 6.8 eV, and the formula for potential energy is 2 times total energy, that is 2 times minus 13.6 into z square by n square, right? So यहाँ से you will get n is equal to 2, right? But the question is not asking the orbit number. It is asking which excited state. N equal to 2, that means it is the first excited state. Okay, that's why option A was correct. Okay, so इस तरीके से you are going to come across such terms while solving questions. Okay, so make sure that you remember these terms. Okay, let me give you one question. This will be more like a homework question because we don't have much time left at our hand. So let me write this question for you. For a sample of hydrogen-like system, what is meant by hydrogen-like system? Single electron system. The energy required to eject electron out of the atom from second excited state is 13.6 eV. Now there are 3 sub questions to this. Identify the sample, then energy of photon, like EP means energy of photon, required to, and इसको आप EV में आंसर करना, energy of photon required to cause excitation of electron from ground state to say second excited state in this sample. And lastly, wavelength of photon emitted when sample de-excites. ठीक है, wavelength आप इसको again angstrom में आंसर करना. When the sample de-excites from first excited state. I'm sure many of you have started giving in the answers. Right, Mihir? नहीं तौसीफ. Like atomic number आप निकालते हो, mass number थोड़े ना निकालते हो based on the Bohr's model. हाँ, बोलो ईशान, you had certain doubt.
Sir, I didn't understand the previous question because your voice was breaking.
अच्छा. Previous question was okay. Let me zoom out a bit more so that everyone can read also. हाँ, इसमें the thing was that you were given the potential energy. ठीक है, तो first of all, don't use the formula of total energy. Use the formula of potential energy, which was 2 times total energy. So you use minus 6.8 equal to 2 times 13.6 into z square by n square. Now hydrogen atom है तो z आपको पता है 1 रहेगा, and उससे आपने n निकाल लिया. So you got n equal to 2 as the orbit number. Correct? अब don't be in a rush to answer B option, because the question is asking in which excited state the electron is present. Right? So that excited state term would mean n equal to 2 is the first excited state. समझ में आया? गौरव, तुमने भी हैंड रेज किया हुआ है?
No sir, it's previous one.
Okay. ठीक है. So I think you guys have started working on getting the answers. Let me share the answers with you, and then maybe we can discuss them in the next class. So the sample will be Li2 plus. When you will do the calculations, you will find Z equal to 2V3. Then the second option ka answer will be around 108.8 EV. ठीक है. And the last option ka answer will be around 135 angstrom. Okay, so maybe somewhere you would have committed a careless mistake. So I hope you guys are able to understand that. Okay. See, aaj ka lecture is something which is difficult as compared to the previous lecture. क्योंकि आज के लेक्चर में मैंने एनर्जी का कॉन्सेप्ट आपके साथ डिस्कस किया है इन बोर्स मॉडल ऑफ एटम, व्हिच आई अंडरस्टैंड दैट मेनी ऑफ यू आर नॉट एबल टू पिक इट अप इन द फर्स्ट गो. ठीक है. सो मेक श्योर दैट यू रिवाइज दिस लेक्चर, reread what has been taught, resolve the questions that were discussed, and then attempt the homework which I am going to send across in the group. ठीक है. So थोड़ा सा इसमें extra effort लगेगा as compared to the previous lecture. Previous lecture was relatively easier, जो radius and speed का था. Energy वाले में थोड़ा extra effort लगता ही लगता है. ठीक है. So अगर आप आज की क्लास में थोड़े से like you were left behind in terms of calculations, so it's okay, that's completely natural, but do put in that extra effort now to make sure that you get it right today itself, and I'll share the homework with you, फिर उसको try करना. ठीक है. All right, any questions, any doubts to be asked? हाँ बोलो तौसीफ.
सर ये जो बोर्स मॉडल था,
हाँ.
इसमें हम लोगों ने वो सेंटर ऑफ मास के बारे में देखा कि दोनों जो न्यूक्लियस और इलेक्ट्रॉन है, ये ऐसा नहीं है कि इलेक्ट्रॉन के अराउंड इवॉल्व करता है, दोनों एक सेंटर ऑफ मास के अराउंड रिवॉल्व करते हैं, दोनों न्यूक्लियस और ये इलेक्ट्रॉन. और आपने बोला कि ये जो सेंटर ऑफ मास है ये न्यूक्लियस के बहुत करीब है, क्योंकि न्यूक्लियस का मास बहुत ज्यादा है
as compared to electron. Yes.
जो ये एक्चुअल जो एक वर्किंग इलेक्ट्रॉन है, उसमें ये न्यूक्लियस सही में कुछ ये किसी एक बहुत छोटे पॉइंट के अराउंड रिवॉल्व करता है, या फिर वो पॉइंट इतना छोटा है कि जो न्यूक्लियस है वो अपने ही पॉइंट पर रोटेट करता रहता है.
नहीं देखो श्रवण, कैसा सर, श्रवण क्या बोल रहा हूँ, तौसीफ इसमें कैसा है दैट we are not able to see electron. Okay. We are not able to do that direct measurement. ठीक है. अब ये क्या था, this was a proposed modification, कि अगर हम ऐसा सोचेंगे तो it might help us explain this observation.
Yes sir.
And that is where this modification, when done, it was able to explain the slight energy differences that were there between the energy levels of plutonium and deuterium. Okay. So this kind of then validated कि हाँ अगर इस तरीके से सोचेंगे तो it will be improvement. it will be an improvement. ठीक है. So
Sir,
इसके आगे भी बहुत सारी ऐसी थ्योरी आप पढ़ोगे जिसमें you can't really directly see the electron doing whatever the theory would propose, but because that theory has proposed certain aspects, certain results
yes,
at a fundamental level, we see them at a macroscopic level, at a like a higher level,
yes.
which validate that theory.
Okay. सर पर अगर पर ये जो सेंटर ऑफ मास का जो कॉन्सेप्ट है इसमें इलेक्ट्रॉन और न्यूक्लियस ये दोनों पॉइंट पॉइंट मासेस है ना.
हाँ,
पर
पॉइंट मास की तरह ट्रीट कर रहा है. करेक्ट.
हाँ सर, पर न्यूक्लियस को हम लोग पॉइंट तो नहीं ले सकते क्योंकि
हाँ
क्योंकि
हाँ, वही डाउट गौरव ने पूछा था थोड़ी देर पहले. Like when we started that discussion, that was the same doubt that Gaurav had asked, and that is where I told him that we proposed here that if we consider them to be point masses and like do this modification, it helps explain
हाँ
this
सर.
observation. So yes,
हाँ
you
सर,
are
पर
right.
अगर न्यूक्लियस एक पॉइंट मास है और अगर ये सेंटर ऑफ मास पॉइंट के बाहर है तो न्यूक्लियस का तो एक्चुअल साइज तो बड़ा
वो कंसिडर में नहीं लिया. We did not take that into account. That nucleus has some finite size.
ओके सर, ठीक.
बोलो प्रकाश.
सर कैन यू एक्सप्लेन दैट काइनेटिक एनर्जी वाला सम?
ये वाला.
यस सर.
इसमें बस इतना ही है सिंपल. काइनेटिक एनर्जी, इनिशियल काइनेटिक एनर्जी और पोटेंशियल एनर्जी का रिलेशनशिप आप बता सकते हो.
यस सर.
पोटेंशियल एनर्जी इज 2 times काइनेटिक एनर्जी विद अ नेगेटिव साइन.
यस सर.
तो इनिशियल काइनेटिक एनर्जी अगर x दिया है तो पोटेंशियल एनर्जी -2x हो गया. इनिशियल
Yes,
काइनेटिक
sir.
एनर्जी x/4 दिया है तो पोटेंशियल एनर्जी -x/2 हो गया.
सर बट इसमें हम लोग ऐसा नहीं ले सकते, मतलब डेल्टा के ही ले लिया उसको, फिर डेल्टा मतलब डेल्टा पी इक्वल्स -2.
कर सकते हो वो
सर
भी.
वैसा भी ओके सर.
बिल्कुल कर सकते हो.
सर और इस चैप्टर के लिए हम लोग मतलब फॉर्मूलाज मतलब एक जगह लिख सकते हैं ना पेपर में, मतलब इजी हो जाएगा हम लोग के लिए.
हाँ हाँ हाँ, फॉर्मूला शीट बनाना will be a skill set that you will need to develop anyways. So if you start doing this chapter, all the more good.
यस सर.
ठीक है.
ओके
बट
सर.
अभी आई वुड नॉट से, क्योंकि अभी हमने लाइक चैप्टर के मिड में ही है. जब पूरा चैप्टर पढ़ लेते हैं, एक समरी जब बनाना होता है, देन दैट कम्स आउट बेटर.
ओके सर. यस सर.
ठीक है.
ओके सर. थैंक यू सर. बाय सर. टेक केयर.
चलो, ऑल राइट. बाय गाइस, टेक केयर. थैंक यू.